All right, let's talk about a piece of tech that is completely reshaping industrial automation. It's called robotic digital twins. And no, this is not just another buzzword. We're talking about a virtual mirror that gives us this incredible, almost magical ability to design, watch, and perfect robots in the real world.
So here's how we're going to break it down. Think of it like we're climbing a ladder, the digital twin ladder, if you will. We'll start with the basics, what is this thing? Then we'll climb through 3 different levels of what these twins can do. After that, we'll peek under the hood to see how it all works. And finally, we'll get to the big question, why does any of this even matter?
First things first, what in the world is a digital twin? Because I can tell you right now, it is so much more than just a fancy 3D model that you can spin around on your computer. Let's start with a big idea. Just imagine this for a second. What if you could build an entire, complex industrial robot, test it, find all the bugs, and make it absolutely perfect before a single screw has been turned or a single piece of metal has been ordered? That's the huge problem that digital twins are built to solve.
And this is the heart of it, right here. A digital twin is a live, virtual mirror of a physical robot. Now, the two most important words here are live and synchronized. This isn't some static, dusty blueprint. It's a dynamic copy, a living, breathing digital version of the real thing, constantly being fed data from the physical robot. So let's start climbing that ladder. First rung, level 1, the prototype. You can almost think of this as the pre-twin stage, before the real robot is even born. And its purpose is simple, but it's incredibly powerful. Virtual design and validation. This is all about getting everything right in the digital world before you spend a single dime or a single minute building expensive hardware in the real world. So what can you actually do here? Well, you can simulate the robot's kinematics, its basic movements. You can simulate real-world physics like gravity and inertia to see how it's actually going to behave. This lets you make sure the robot can reach everything it needs to, and, this is the big one, it ensures the robot won't crash into other machines. Getting this right at the start, saves an unbelievable amount of money and headaches down the road. Okay, up to the next rung, we're at level 2, the digital shadow. And the key concept here, the one thing you really need to get, is one-way data flow.
Just think about your own shadow. It's the perfect analogy. The physical robot is now built and running, and it's constantly sending a stream of data to the virtual model. The model mimics the real robot perfectly. But, just like your shadow, the model can't influence the real thing. It can't talk back. It's a one-way street of information. And this is where things get really useful. It means you can remotely see exactly what the robot is doing in real time, from anywhere. You're not guessing. You're seeing its precise position, the temperature of its motors, even how much torque it's using. It's like having a perfect live dashboard for your machine right on your screen.
And that brings us to the top of the ladder, level 3, the full twin. This is the holy grail. This is where we unlock that powerful two-way data flow. This right here is the real game changer. It's not just a one-way street anymore. It's a fully integrated system where the virtual world and the physical world are in constant conversation. They don't just mirror each other, they actively influence each other. And that two-way communication, that's where the magic really happens.
So what does that actually look like? Well, you could test out a new, more efficient movement in the simulation, and if it works, you can push that update directly to the real robot's brain, its PLC code. Or, let's say, a sensor on the real robot detects a tiny vibration. That can automatically trigger the twin to run hundreds of what-if scenarios to figure out the problem. This is how you get to true predictive maintenance and next-level optimization.
All right, so we've seen what it can do. Now let's pop the hood for a minute and see how this thing actually works. A really deep digital twin is built on 4 distinct layers. Think of it like a tech stack. At the very bottom, you've got the physics and kinematics engine. That's the foundation that handles movement and gravity. Then you've got the virtual PLC, which is basically a digital copy of the robot's brain. The third layer is connectivity, the nervous system, using things like IoT to link everything together. And at the very top, you have the analytics and AI layer, the superbrain that does all the learning and optimizes.
Now, that virtual PLC layer is absolutely huge. Just listen to this quote. You can debug your M580 code 100% in the office. This is virtual commissioning. I mean, think about that. Instead of spending days on a loud, cold factory floor trying to fix bugs, you can do it all from your desk. You show up on site with code that you know works because you've already tested it on a perfect virtual copy of the machine. It's an incredible time saver.
So, okay, we've climbed the ladder, we've looked under the hood. Let's put it all together. Why does this technology really matter? What's the actual real-world payoff here?
I absolutely love this analogy. When you put the digital twin on an operator's control screen, you're basically giving them X-ray vision. You know those big robotic cells surrounded by safety cages? You can't see what's going on. Well, now you can. You can see right through the metal and understand exactly what's happening at any given moment.
And this isn't just a cool visual. Look at these practical uses. With predictive maintenance, the twin might notice a motor is running just a tiny bit hotter than it should be and flag a potential bearing failure weeks before it actually breaks. You can perfectly simulate and sync up the complicated dance between a robot and a moving conveyor belt. You can even track the energy used by every single tiny movement to make the whole process greener and cheaper.
And this is where that top-level AI layer flexes its muscles. We're talking about the twin running thousands of what-if scenarios automatically in the background. What if we make this movement a little faster? What if we change the path just slightly? The twin can figure out the absolute best, most efficient way to do a job without ever putting the very expensive physical robot at risk.
So let's put it all side by side. This really brings it home. A basic simulation, you feed it manual data, it's done after the design phase, and you're just hoping it works. A deep digital twin, it's fed by live data from the real world. It lives and learns for the entire life of the robot, and its purpose is to constantly optimize and predict. It's the difference between a static blueprint and a living, learning digital organism.
Which leaves us with one final, kind of mind-bending thought. As these digital twins become more and more perfect, these flawless virtual copies that are constantly talking to and changing their physical half, where does the real robot's identity even begin? Something to chew on. Thanks for tuning in.